of what an equivalence relation is. It has to satisfy those three properties, that it's reflexive, symmetric, and transitive. Okay, so a new concept now. The idea of an equivalence class. And what's meant by class here is it's basically just a set. Right? So you can talk about an equivalence set. So the definition of an equivalence class is it's the subset. You have a class A, right? And you have an equivalence relation on the members of A. So an equivalence class, or an equivalence subset, if you like, it's a subset of A, and all the members of that subset, they're all equivalent to each other. Okay? So here I'll putting that another way is if you give me just one element of the set, so A is just a member of big A, it's just one element, then the equivalence class of that element, little a, is just the set, or the subset, of all the elements belonging to this big set, all the elements that are equivalent to it. Or put it another way, it's the subset of all the elements, X, where there's an equivalence relation between X and A. Right? So in other words, it's the set of all X's, and all the X's are equivalent to A, which is a kind of shorthand way of saying that X and A, there's an equivalence relation between these. So an equivalence class, that's the usual term, not like an equivalence subset, but that's what it is actually. But this is a standard term, an equivalence class. It's just the subset of elements where they're all equivalent, and they're all equivalent to, let's say, this element A. So you talk about the equivalence class of A, little a here. Little a, it's an element, right? It's the subset of all the elements that are equivalent to this little a. That's an equivalence class, equivalence subset. Okay, right? Well, now that we understand, I hope, the idea of an equivalence class, we can now do our first theorem for this lecture, for this session, right? So it's Theorem 55 in your text, page 55. See if I can find it quickly. It's on page 154. If you have the text, page 154, right? And it's in two parts. Then the first part is for any element belonging to your set A, big A, then that element belongs to its own equivalence class. Now what is this? Remember this A bar, with a bar above. It's this, right? The three lines here mean by definition. So A bar is just the set of all elements of A, well, subset, where X has an equivalence relation with A, with this element A, right? So this is just saying that A belongs to its own equivalence class. So this set here of all these X's, one of them will be A. One of these X's in this subset will be A. So A belongs to its own equivalence class. Maybe that seems common sense, but we'll prove it in a minute. All right. And the second part is if there's an equivalence relation, if A is equivalent to B, so these are just two elements of your set A, right? So if A is equivalent to B, in other words, there's an equivalence relation between A, little b. If that's true, A is equivalent to B, if and only if, so both ways, the equivalence class of A is the same as the equivalence class of B. Now what is it? This is a set, well, a subset. This is a set, right? Like, it's here. It's the set of all those x's where x and A have an equivalence relation. So it's all those x's that are equivalent to A. And this one, B, it's the set of all your x's where x is equivalent to B. Right? So what you're saying is, if A is equivalent to B, if and only if the equivalence class of A and B are the same. So these two sets are the same. All right? Well, let's prove the first one. Now, this tilde here is an equivalence relation. Right? So we're trying to show that A is a member of its own equivalence class. So now A is an equivalence relation, and therefore the reflexive property is true. Right? Well, all three are true, but that includes this one. So x tilde x, so x is A, so A tilde A, right? A tilde A, and that means that A is one of the members of A bar, right? I mean, to be a member of A bar, you have to have an equivalence relation with A. Well, A does have an equivalence relation with A, so A is a member of this, right? Because if x is A tilde A, but A tilde A is true because this tilde here, this equivalence relation, is well, it's an equivalence relation. Therefore, it's reflexive. Okay, A tilde A. So therefore, A belongs to its own what's the word? Equivalence class. Right. So we've proved that. All right. Now it gets a bit harder. So it's an if and only if proof. Right. It's a two-part proof. So as usual, we'll start with the if part, strong convention in pure math. So A tilde B if these two equivalent classes are the same. Now A if B, P if Q, therefore Q is if Q then P. So we start with the right hand side, which is this, and we have to prove that. That's the if part. And then the only if, that's the other way, that would be starting with the left hand side and proving the right hand side. So starting with the if, we start with this and we have to prove that. Okay? So here's the if part, here's the only if part. So for the if, we have to show that if the right hand side here, that's this, these two equivalence classes are equal, so these two sets, remember an equivalence class is a set, well, it's actually a subset of big A. So these two sets are equal. So if these two sets are equal, we have to prove this, that A tilde B. That in other words, there's an equivalence relation between members A, elements A and B. Right? So given that, prove this. Right? Here's the proof. So if A bar equals B bar, so the equivalence class of A equals the equivalence class of B. Now these are just two sets, remember? They're sets. So if that's true, then obviously this is true. So this set is a subset. You know, it's a it's a subset of B, right? If they're equal, they're a subset of B. So A is a subset of B or equal to B. So if that's true, that's obviously true, right? Now from part A here of Theorem 55, A belongs to the equivalence class of A. Right? That's what we proved here. We just proved it here. So A belongs to its own equivalence class. That's what this says, right? So A belongs to that. So if A is a member of this set, and this set is a subset of this one, then A belongs to this set, right? A bar is a subset of B bar, and little a belongs to A bar. Therefore, little a belongs to B bar. That's like the superset, that's the subset. Okay, so A belongs to B bar. Now, if A belongs to B bar, that means, now what is B bar? It's just the set of all, so if this is B bar, you'd have, it's a set of all these x's where x tilde b, right? So, so if A belongs to that equivalence class, by definition, then A tilde b. For A to belong to this, you must have this equivalence relation going on, A tilde b. Right? So we know A's tilde b. That's the left-hand side. So we've proved this. So we've gone this way, gone from right to left. Okay, now the only if, go the other way. So we start with the left-hand side, and we have to prove the right-hand side. Now, a little bit of discussion on global strategy. So we're starting with this, and we have to prove that two sets, remember these equivalence classes, they're both sets, so we're trying to prove that two sets are equal. Now in general, I've done this quite a few times now, how do you prove that two sets are equal? By showing that one is a subset of the other, and the other is a subset of the one. So it's like a two-part proof again, inside a two-part proof, right? Okay, so we have to show that A bar is a subset of B bar, and B bar is a subset of A bar. And then put the two together, and therefore they're equal. Right? A general proof on how to show that two sets are equal. You use the concept of subset, right? Well, let X belong to A bar, right? So we're trying to prove that A